Welcome back, everyone. Going to get started. So the last session of day 2 concerns a topic that we've kind of been discussing on the margins since we got going, and that's emerging technologies. The caption is the balance between legacy and innovation. Our moderator for this session is Mr. Filippo Tomasello, whose career spans decades in the Italian Air Force, ENAV, the Italian Air Navigation Service Provider, Eurocontrol, the European Commission, and more recently at EASA, where he was a rulemaking officer developing rules on ATM, aerodromes, flight operations, flight crew licensing, and airworthiness. He's a senior partner and technical director of the Italian branch of USC, an aviation consultancy offering services in RPAS. And he's an active participant in the RPAS panel. Filippo, thank you for joining us, and I'll turn over the session to you. Thank you.
Thank you, Philip, and of course thanks to ICAO not only for having organized this symposium, but for having given me the honor of being moderator of a panel with 4 of my colleagues. Thank also to the Sichuan provincial government for having sponsored and promoted the organization of this event. And thanks also to my friend Mike Lissone, which abstained from being a speaker also in this panel, so at least for 2 hours he can relax and we will hear different voices. So we have a problem, as we have seen during these 5 days. UAS are a very dynamic area of technology. There are new inventions every week, but our problem is the same problem which Leonardo da Vinci had in Italy more or less 4 centuries ago. If you remember, Leonardo had sketched the idea of the helicopter with something rotating at high speed in the air. The idea was excellent. It was an invention. But to translate the invention into an innovation with an impact on our lives, it took more than 4 centuries. Because there were no internal combustion engines at the time, no metal alloys strong enough for the centrifugal forces of the rotor, no gearboxes able to connect the engine and the rotor, and other things. Let's hope that for us it will not take 4 centuries, but now in this session we will see that enabling technologies are emerging, and then I would kindly invite the floor to send any questions on the technologies, but also on their perception, how we can transpose these inventions into real operational life. During the panel, the speakers, please come here, will be the 4 colleagues that you see next to me. Monsieur Pierre Fossier comes from France. He is vice president at Thales in the business unit Land and Air Systems. He worked 15 years at Dassault Electronique, and then in 1998 he joined Thales, where he has served in avionics programs for both military and civil aviation, but not only avionics, even ground systems and space-based systems for air traffic management. Now he is also, in addition to Thales, member of the steering committee of the French Orientation Council, not only for UAS, but for civil aeronautics research, and vice chairman of the French National Foundation for Research and Aeronautics and Space. In his presentation, in few minutes, I have understood that he will speak mainly about avionics, flight control, navigation, sensors, but also of a new idea about the so-called convergence between manned and unmanned aviation. Pierre, have I understood?
Yeah, thank you very much, Filippo, sorry. Yeah, the purpose of my talk today is to talk about technologies for our past, and you know, there are cutting-edge developments in aerospace technologies for our past, both on legacy technologies or on specific technologies. But the other idea I would like to introduce with you is that because of the scope of possibilities of our past, actually the ARPAs create new avenues for the manned aviation. In fact, we can say that ARPAs paved the way for the future of aviation, and I will illustrate that with 3 breakthroughs, which are artificial intelligence and digital technologies, automation and autonomy, and finally UTM and ATM. So yes, I will talk about avionics, but a little bit around UTM as well.
Thank you, Pierre. You will get a seat, kind of. Then the next colleague speaking will be Fredrik Nordström. Closer. Otherwise, the audience does not see you if you don't stay closer. Fredrik is, as you can see, is a young, tall, slim, handsome boy, but although he looks very young and nice, he has more than 20 years of experience in UAS. He started his career as engineer from the Royal Institute of Technology in Sweden, and then he immediately went down to Germany, which was a bit warmer and brighter than Sweden, working at Daimler-Benz Aerospace. Then this company was purchased by Airbus Defense and Space, including you, as I understand from your bio, and he was their system engineer for the concept design department in UAS, and later he became a chief engineer of that department. In 2008, he moved to the Office of Airworthiness, was involved in certification of different ARPAS programs. He gave me troubles when I was in EASA, because the German regulation covered UAS up to 25 kilos, and EASA down to 150. And he had a machine of 70, 80 kilos, which was orphan. And so he came to me and crying. Anyway, now he represents industry in the ICAO ARPAS panel, appointed by the Aerospace and Defense Industries Association of Europe, ASD, which is inter member of ICAO, the International Coordinating Council of Aerospace Industries. And congratulations, a few weeks ago, he has been elected chairman of the ARUS Stakeholder Consultation Body. He will speak about everything: high-altitude pseudo-satellites, unmanned cargo, urban mobility, UAS traffic management. You want to say something about it?
Thank you. Thank you, Filippo. Good afternoon, everyone. It's a pleasure to be here, and thank you very much for the arrangement. It's a very good one. Some corrections. I'm not that young. I'm turning 50 actually in November, so I've been around a little bit. I used to say that, well, I was born 68 and 69 we landed on the moon, so I went through a lot of things, good stuff. I wish I could have done that landing, but all right. So, yes, I will. Tonight I have different hats, but tonight I will represent Airbus, and not ICAO and not ASD, so it's Airbus. I will talk about what Filippo said about flying cars, and I will talk about parcel delivery, what we're doing, and a little bit about UTM, but I will do it very briefly. and because the main issue of this panel is to find gaps, especially regulatory gaps and challenges that needs to be worked on further. And I will take the opportunity also to say something about what has been accomplished or released last week from Airbus. Thanks to Altiscope and the team of Yusuf Mowbray, who's sitting there. We have released our vision of UTM and integration of autonomous UAS. And if you, this is it. You can find it also on the webpage of Altiscope. And I think that perhaps there are some copies also available for you. Thank you.
Thanks, Fredrik. Then, so far you have seen in this panel 3 Europeans. But Miss Carey from ICAO tells, don't forget, ICAO is global. It should not be European-centric. So in my panel, I have also the pleasure of having Professor Hyunchul Shim. If my pronunciation is not correct, I will call you David, which is easier. He is Professor of Electrical Engineering in KAIST in South Korea. He is also Director of the Korean Civil ARPAS Center, which is in charge of integration of ARPAS into Korean airspace. He also is the leader of the Intelligent UAV Research Laboratory. Congratulations to be intelligent. I am still trying to get there, but I am unable. You also serve as government-appointed advisor in the ICAO ARPAS panel, and in addition to that, is an expert in the artificial intelligence and robotics for the World Economic Forum, and also is advisor to the United Nations in Geneva for lethal autonomous weapon systems. You know that in our domain, we have a lot of acronyms, RPAS, UAS, someone says UAV, UTM. So why not to introduce a new acronym, UAM? If I understand, you will speak about UAM and other things, David.
Thank you very much, Filippo, for the nice introduction. As he mentioned, I've been attending the ICAO meeting for the last 3 years, and it's a great honor to talk here in more detail soon. And the topic is very interesting, and I was very excited to hear that I have a chance to talk about my research, other people's research in the emerging technologies. Normally, ICAO, as mentioned many times today or even yesterday, we have to be on conservative side because of the safety, and it takes a lot of energy to move the huge inertia of the ICAO to embrace new technologies. For today, 15 minutes for my talk, I'll talk about some outrageous things about the AI robotics that may affect our aviation in a few years or even maybe tens of years to come. So I'll present that kind of thing. Thank you very much.
Thank you, David. And of course, in China, we need to have at least someone bringing the voice of this big country. And this is Mr. Wang Yufeng, which you may call Alex. He is in charge of the Wireless X laboratories at HUAWEI, and is mainly responsible for research, incubation of the industry ecosystem, cross-industry solution architecture design in relation to applications supported by the 5th generation, 5G, of the mobile radio telephony. He has joined HUAWEI in 2001 And there he has been involved in development of new wireless solutions, offering strategic planning, industry promotion and expansion. He has held a number of important positions, such as engineer for R&D wireless solutions, chief engineer for such solutions, and then director of the CDMA and LTE marketing support department. And now he is director of the MBB solution marketing department. And I understand that you will speak mainly about communications, correct?
非常高兴能够作为中国人的
introduce me. But why did I come here? I have 15 minutes. Actually, for HUAWEI company, this year we identified our vision, which is to bring the digital world to the individual family and organization. We want to build an IoT world. So we are thinking what kind of worlds can be digitalized. The first thing that popped up in our mind is the sky, because the sky is very similar as digital space. Because we talk about aerospace. It depends on how we identify it, how we define it. Without definition, it's nothing. With definition, it's a completely different world. That's why, as a communication company, HUAWEI is committed to such a technological revolution. We hope that later in my speech, in my presentation, you can have a better understanding of how we can redefine the sky services that we have now with the communication technologies and what are the possibilities. Thank you very much.
See, Alex. And now the first speaker in our agenda is Fredrik. So if you kindly take the floor, the audience is curious to knowing what you want to say.
Thank you, Filippo. So, there we go. So we'll start my presentation talking about very high altitude operational systems. After that, I will talk about low or even very low altitude operational system finalized with some examples of gaps and challenges with respect to regulations that we see. So, starting with the high altitude. What Airbus is doing, we have Fossier, who is a pioneer in the, there it goes. In high altitude and long endurance operations, it's the world leading solar electric stratospheric unmanned aerial vehicle. It flies above the weather and regular air traffic, covering very large distances and is in the air for weeks, actually. It is used especially for surveillance and communication. It is using a centralized mission control center where one pilot can operate several vehicles at the same time. Airbus has already performed such operations and continuing to develop such concepts, taking advantage of our experience in satellite operations. It's a very slow vehicle, 50-60 knots, limits the maneuverability. It's rarely at constant altitudes. It climbs during daytime and descent during nighttime. It's very much affected by wind, so it may not follow a precise track. And it's of course not fully IFR compliant. So it should be said that we do this performance today using the risk-based approach, taking the total operation with environment into the consideration. So the operations are very much different to the current scope of ICAO RPAS panel. We have seen in the presentations yesterday that ICAO has started to work on categorization and risk assessment, and there is in ICAO also a space learning group, also which has taken on these tasks, and it's very much appreciated. And later this week, because I will not go into much detail in this one, a colleague of mine will present more details on HAPS, especially Fossier and its operational characteristics and how we are dealing with it today and how we see that we're going to do it in the future. I just wanted to highlight some of the gaps, such as you mentioned, the pilot operating, several aircraft, we have autonomy, we have electrification, we have DAA, and we have traffic management. The next topic I would like to talk about is urban air mobility. So as you know, the cities today are getting more and more crowded. We all know that, and transportation is getting more and more demanding. So we have new exciting technology advances in aviation, and actually the science fiction of flying cars is on the way. And in many ways, we will see vehicles in which there is no pilot on board, and the passengers are transported under the supervision of a central station monitoring and controlling several vehicles at the same time. Also here we can identify challenges such as autonomy, electrical power, and detect and avoid, but also find configurations like multi-rotor configurations which are beyond the current scope of the ICAO RPAS annexes, Annex 8, which is only covering helicopters and fixed wing. And not to forget, for these kinds of operations, UTM will be an essential part to make this happen, and I will talk a little bit more about that later. Another thing is aerial cargo. So it's another example of a non-traditional aviation, also mentioned several times today, and low altitude performed by the drones. And here also UTM and automation is for sure the enablers. We had Airbus, we have the Skyvex project in Singapore, who is developing the capabilities of cargo deliverables by drones. It is designed for transporting of transport in urban and non-urban areas. The next one, UTM. As we all know, UTM is a key enabler technology for unmanned commercial operations like the previous mentioned drone cargo delivery or even future air taxi services. So without UTM, these things will not happen. Making everyone cooperative is making integration a lot more easier. That's why we also recognized already several years ago that airspace classes A to C should be the starting point. And the current scope of ICAO IFR international flight was a very good starting point, we do believe. However, several regulatory and standardization initiatives have started working with UTM, but there is a lot to do and it's just a starting point. And eventually, we also need an international harmonization of that. So, summarizing some of the products we have from Airbus, we have Altiscope. The Altiscope project is a simulator for evaluating policy options and operational models for air traffic management systems that can service all forms of airborne traffic. And we will hear more about that later this week. We have City Airbus, development of a multi-passenger, self-piloted electrical vertical takeoff and landing demonstrator designed for urban air mobility. We do have Vahana, which is development of a single passenger self-piloted electrical VTOL, developed to open up the urban airways. We do have Skyways, of course, the collaboration with Airbus and National University of Singapore to test the delivery of small parcels using UAS. We do have also VOOM, which is an on-demand service that allows to book a helicopter on a shared basis via the mobile, perhaps something for the future flying taxis. So coming to the key points where we see that we especially need to do some, to make some special attention on, I think that's nothing to argue about. It's UTM, and especially a performance-based UTM, because as stated before, it's a way forward to enable aerial cargo and urban mobility. There will be different aircraft with different integrity and capabilities which requires a flexible way of integrating them. So there is a need for a sort of performance-based or risk-based UTM system taking into account the environment, the system, and the different ways of operating. The next one we do have is detect and avoid. Detect and avoid and separation is also a topic for very high operations and very low operations, of course. And in some cases, we can today operate safely without an onboard system. So it is segregated or quasi-segregated, but this limits, of course, very much the operations. Here we see also UTM as a potential enabler by making them cooperative and hence ease the burden for onboard equipment. I think that will be one of the topics also for the drone enable. So especially smaller aircraft, we found out, have issues of carrying the detect and avoid systems ongoing in the standardization processes, because these systems required to reach the ranges requires radars which are quite heavy and definitely not possible to integrate on smaller aircrafts. So here we see DAA needs to be treated more in a combination with a traffic management system in order to reduce the equipment needs in the aircraft actually. So we need a new way of thinking about detecting and avoid for the smaller or smaller aircrafts. We have what mentioned already several times this week, autonomy or even AI will be key enablers for especially urban air mobility. But as for all new technologies within aviation, we need to keep at least a good safety records as of today, and of course the goal should be to even increase it and doing it even better. But for that, we need new standards and regulations. It is recognized that autonomy and AI are at a very early stage, but it is not too soon, I think, to start work on regulations and standards. But of course, it will be required to have a stepped approach. And it is not only technical issues needs to be solved, there's also legal and public acceptance issues that also has to be discussed. And autonomous UAS are not today within the scope of ICAO, and the question is perhaps could be in the future, because eventually there is a need to establish international harmonized regulations, and there is an opportunity for ICAO to take this topic on board actually. I mentioned also electrification, and there are other configurations and systems like multi-rotor, etc., that needs also further attention. So far, ICAO Annex 8 amendments proposal is only covering helicopters today, for instance, and not explicitly also not fully electrical aircraft. So there is some work needed to be done also in these areas. I mentioned also before one operator controlling several UAS or RPAS. So as seen from the presentation, many of the new operations are requiring that one pilot can operate several vehicles at the same time. It is fully understood why the current scope of ICAO international IFR operations is not allowing this for the time being, but for the future this will be required to be able to take full advantages using RPAS and UAS. Point number 6. We need standardized risk-based approach. We talked about it a lot of times this week, and I think many of us see the risk-based approach, and they have performance-based approach and different names. We need that as an enabler to integrate systems cannot do what we traditionally expect that aircrafts should be capable of doing. So, but risk-based does not mean that the risk is increased and lower the safety. Risk-based means that the total environment of the system is operating in is taken into consideration in safety assessment. So, but to be truly effective as a means, as I stated before, risk assessment must use a common methodology so that they can be used between services and the authorities around the world. One example is, of course, SORA from Yaros, and we at Airbus, we are using SORA in several projects and also in different countries. So the work done by Yaros and SORA is highly appreciated, and it's of course a development process, and we hope that that will continue, because risk-based approach is key to integrate innovative UAS systems. We did hear yesterday that ICAO has started discussions on risk-based approach, and I think that's good, but it would be beneficial if perhaps a task force or something like that is established between ICAO and Yaros to harmonize the work a little bit. And furthermore, of course, there's a lot more topics, but I think these 6 ones are a good starting point. And I hope this presentation gave you some food for thought. Thank you very much.
Thanks, Fredrik. So I don't know whether in the audience everyone remembers that in ICAO we have a concept of operations for ARPAS, which is a blueprint of the current standardization effort in ICAO, which does not cover flight at very low level, below 500 feet, does not cover flight at very high level, above flight level 600, does not cover autonomous operations, does not cover carriage of passengers, does not cover autonomous operation, maybe I have already said. And one of the dogmas is one pilot, one aircraft, not one pilot and several aircraft. Fredrik has more or less said that the industry is going beyond more or less in any direction, in all these directions. So if you have any questions, you have the app. Please raise the apps, and instead we go to the next speaker, which is David from Korea. Is he? Are you the next speaker, David? If you want. And so we continue to analyze these new frontiers of technology.
Yeah, thank you for the introduction. So I'd like to talk about the emerging technologies as shown in the screen. So I'm leading the Korean civil ARPAS integration effort, and Korea does have a very strong UAV research and integration programs going on. One is ARPAS part, and the other is UAV part. The other one is led by Dr. Kang, who's actually in this room. I hope we can present some time in the future about our effort. But today, I'd like to talk about more of the emerging technology part of AI and maybe some mobility beyond it. So, so in this picture, I showed our aircraft, the CTLS-based OPV, optionally piloted vehicle. And so the AI, artificial intelligence, we talk about it a lot, and then especially these days, machine learning, which is the latest craze in AI. There are other forms of AI, but the machine learning has been shown quite effective. So the image classification is one of the most successful applications of machine learning, and the latest machine learning-based image recognition outperforms humans. And it was the record was set back in 2012, and that may indicate that AI, if we ask AI to do the vigilance for pilot in case they are doing something busy, and then maybe we can get a better result for detecting a void. Of course, there are a long way to go, but if we only look at the specific task, maybe computer can or AI can outperform humans and without getting tired or distracted. And as the AlphaGo shows, AI can make some limited strategic decisions. And with this faster computing and the enormous amount of data storage, AI-powered autopilot may be developed, and which can help the civil aviation greatly. When the AI is applied for not safety critical applications, they are being adopted in a very extreme phase. For example, many of you may have the iPhone 10, which has Face ID, and it is known to have the mistake rate of the 1 millionth. And then AI speakers, sometimes they do funny things, but many times they can be useful. And then China, I was told that you use a facial ID system for the financial transaction system and more. But of course, I've been attending many ARPAS meetings so far, and I know very well that the safety, civil aviation safety is of utmost importance. So the AI ecosystem just cannot be introduced that easily. So the some insight of AI, I've worked on this AI for the application of the UAV drone detect and avoid or target detection. And the deep learning, I'm limiting my scope on the deep learning based, and it is drastically different from previous AI systems such as expert systems, and then it requires a huge amount of data. So if there's no data, no learning, and you don't know the things. And currently AI can be applied to relatively simple tasks, but AI does not constantly learn in contrast to certain misunderstanding. Of course, there are researches on what they call lifelong learning, ongoing learning AI, but what they are using right now is that we learn offline because it requires a tremendous amount of data, computing time, and then we freeze it at the stage and we use it. So we learn and run, so they don't really mix. So you don't have to worry about AI picking up wrong thing during the operation, but in the future they might be doing that. For right now, we don't do that. So it is true that the inner working of deep learning is not clearly known. So it is more of the empirical system, if we will, that we know is working, so it is working. The AI-based systems are different from adaptive systems, and adaptive system is a system constantly changing. Back in 1990s, original my background is control engineering, and there is adaptive control, and which was a big issue for aviation industry because the adaptive control cannot be easily certified because once you certify it, it constantly changes. But AI is a little bit different from them. And also the learning-based system can be quite sensitive to small changes because it's a highly nonlinear system. For example, if you change the brightness a little bit, if you introduce certain disturbance in the image, it may do pretty bad results. So the AI can be used, for example, if deep learning can be used for civil aviation in terms of the DAA system, which is a working group I'm attending. And I've been attending DAA for our ARPAS. We are interested in the international IFR flights. So we don't really need to have the vision-based system. And also vision doesn't really work very well in IFR situation where you don't have the very good condition. There's a cloud or a nighttime, you don't see it, but human is using vision mainly a primary source of the information. And also when later on, the US is already doing it, but if you are looking into the RPAS operating in the VFR airspace, then you may need to have those things. So we can have we can collect a lot of the annotated data set, and then we can train a neural network to the work. And then in latest GPU technology, real-time detection can be performed pretty well. And you can see that in this particular picture, you see airplanes seen, and there the red bounding boxes are drawn around it, meaning that they are detected pretty well. So this is too much detail. I'm not going to talk about it. And but we use what they call the modified SSD technology, and we detect the image on the shot. Actually, the lower right image is a video. I hope it works. But can you click over there? Anyone's listening? Can you click? I set it to autoplay, but maybe the correct is not working. So if you have a hard time, I'll just skip. So this video is supposed to show that, okay. Yeah, it is playing, but not quite updating. But it is supposed to show that an airplane is passing by, and then we have this red bounding box appearing around it. So what is the detection rate? We don't really have a very high rate, unlike the Apples, like they have 1/1,000,000th of the, okay, there it goes. So with the background showing, we have the aircraft pretty well defined, well detected within the background. So we need to train the neural net with all different situations. So, okay, that's the, I think that's a video coming from the Reno's air race. So these are the still shots of the aircraft being detected using the deep learning. So we may be able to use this thing for the VFR situation, DAA technology, although right now we are writing SARS to use the transponder-based, ADS-B-based, TCAS-based, and the dual regard radar on board. But the radars are expensive. So they may be, if you later on you can use the VFR, then this kind of vision basis is working pretty well. This is pretty recent work, and what the learning doesn't do very well is that it detects a shape. But when I have to joke here, when I first worked with my students, and they initially applied this to the large aircraft images, and I joked them, if you see this, you're already dead in the aircraft. So you need to detect the small dots. So that's it is a different work. But I have to clarify that I saw the one recent NVIDIA's work that they do detect a large aircraft or even the partial part of the aircraft to detect the ground traffic in the airport. So that I think that's still valid work. But in our specific scenario, we like to use the DAA, the deep learning-based DAA for the long-distance detection. So this is a video. You can see that there are airplanes being moved on the runway. There's another aircraft approaching in the runway, so we can detect it. So so you can see the small dots there. So we can expand this work to detect the multiple aircraft or all these things. So this is another shot. We use a GoPro camera attached on the cockpit, and we try to detect the incoming aircraft on the traffic pattern until it finally touches down. Okay, so this is another interesting part. So if AI can be used for certain detection, can you use more of the AI to have the smart pilot? So what about, so there was a DARPA research, and the DARPA was interested to use a robot to partially aid the pilot. So that's the left side, lower left still image is the US work, I think it's Aurora aircraft, and the right side is the robot trying to mimic the pilot's the motion to try to start the engine and do all the things. So, and the left side is using only one robot arm. The right side is we do have the humanoid robots do all the things. He's trying to start and all that. So I don't think I have a time to show the entire video. It is on the internet. If you have, you can access, you can see it. And in the lower right, that is the SBIR the announcement by US Air Force, and that they are looking for the humanoid-based robot pilot. Actually, they cited my paper to do this interesting work. Okay, so it's a little bit long shot. Many of you wouldn't agree with this, but human pilot is, we all know there are good things, but so far I like to say that there was no alternative. All the aviation was built around the human pilots, and there's no way denying it in the near future. But what if there's a robot pilot, and then that can be really a robot, or it can be a box with a software with the internet connection, onboard connection. So the robot, definitely, there's long lines of things. I cannot read everything, but if you read them, they are complementary. There was some wave of robotics that we can completely substitute humans, but the latest approach is not substituting it. We are trying, roboticists are trying to complement the human capability. Suppose a pilot has a very difficult time with overload work, then we can help the robots. So I'd like to summarize. The future of AI is civil aviation. It needs a long time before the adoption, but it is essentially interesting direction and maybe effective too. And then a robot pilot can be used in many different ways. And then I think Fredrik already mentioned, but we really need to have a novel way to certify them, because this is a very different animal. So we cannot really certify this in a more conventional way. So we have to come with a new way of certifying it. So this is barely starting, but without really knowing it, the AI is already used in a lot of applications every day. So I think the aviation soon, we can get some benefit from it. Thank you very much.
Thank you, David. So this is not science fiction. If I have properly understood, because I am not a specialist in this area, round the corner we have machines which are able to learn, and these machines are more or less like safety management, because David said in one slide, no data, no learning. The same principle of proactive safety management. However, these machines will have a behavior which is not deterministic, which may raise a lot of issues for liability, legal aspects, and certification. So if you have any questions for David, please use the app and send them. And meanwhile, I will give the floor to Monsieur Fossier. Pierre, if you kindly deliver your speech, the audience is curious to knowing something even from you.
Right. It's good news because I thought I was the last speaker, so I'm not the last obstacle between you and the dinner, so that's good. As I said in my pitch, I will sort of elaborate on 3 breakthrough avenues. But before, let me go into a quick summary of the technologies for RPAS. So the first thing is we have a lot of legacy technologies applicable to RPAS that come from aviation. I will not go into detail on that slide. I could add other domains like energy management and electrification, as was said before. The point here is, whilst you might say, well, this is an incremental evolution of legacy technologies for RPAS, actually that requires a lot of effort for, in particular, reducing size, weight, and power. So we are continuing, although it's legacy technology, to work on this one. And of course, we could swap C because of cost and increase performance. Apart from that, you have technologies which are specific to RPAS. For example, that's not a comprehensive list here, but you know well the 2 first one, sense and avoid or detect and avoid, automatic takeoff and landing. We know the importance of communications, but here we begin to tackle not only the technology, but also the regulation, which frequency, the spectrum, the quality of service, the use of satellite communication, but it begins to be something which is very specific. And the three bottom ones here are very important because security has to be embedded natively. Why? Because in an aircraft, you have got a bubble around the aircraft. The only link is the pilot via the communications, but with RPAS, you need to open that bubble encompassing the ground, so it's permissive to intrusion, to jamming, so security technologies and cyber security is quite important. And the two last one here are very important because you need to certify, you need to ensure safety, you need to ensure airworthiness, and you come to not only flight management, but mission management. And the small vignette you have here is an example of a mission management board for UAVs. And believe me, even for a 2 kilograms UAS, this is worth several millions lines of codes and worth several tens of millions of dollars of development. So that's paramount effort to develop these. So a strong innovation must be sustained, but here, not only a technology, on regulation, and on procedures. So, the three breakthroughs I wanted to insist upon are the following. First of all, digital transformation. You know that by heart, we're coming in a digital era. What does that mean? It means that the value is in data, not in the equipment that gathers data, but in the data itself. And I will show why UAS are very important in the frame of the digital transformation. This next one is, and I will develop that, in terms of automation and perhaps up to autonomy, I think RPAS, or US in particular, but we see RPAS, can pave the way for the future of manned aviation. And the third one, which is the consequence, is the ground aspect of that, which we call UTM, unmanned traffic management, cannot be a simple legacy or continuity of ATM. And actually, we believe UTM will transform ATM at a certain point in time. So let's develop these three aspects. First of all, digital transformation. To focus on technologies, we believe that there are four main technologies for digital, which are connectivity, IoT, that's where you gather data. Big data, you collect them. AI, as said by David, where you extract significance in the data, helps you make decisions. And of course, you have to put cybersecurity in it because the value is in data, therefore you need to secure the data, all right? So what I'm going to do now is to focus a little bit on AI. Thanks, David, for putting the landscape for me, and I think we're quite in line on this one. Why is AI important for our path? Is because it's a strong enabler to take decision, to plan and decide, all right? So historically, there are two categories of AI. Model-based AI, where the knowledge is inserted in terms of models, and the data-based AI, where you introduce data. And as David said before, this latter has experienced a lot of progress in what we now call deep learning, i.e. the ability to gather a lot of real data to extract significance out of this data. Right, now there are some challenges, and again, David has better than I describe all the challenges associated to AI. You have to trust, you have to secure. Learning is key, you need data. So we would like to have frugal learning, i.e. not necessarily wait for a lot of data to be gathered. How do we learn? Do we use real data, synthetic data? How do we balance? And of course, there are vulnerability of neural networks because you don't want that to be spoofed. The concept, and again, I must apologize, I will not develop that too much, is explainable AI. There are techniques which we're working upon, which result in combining the two classes of AI, a reasoning engine that program explainable AI, which is an important avenue to have trustable and even certifiable AI. Right? So keep in mind, this is a strong avenue to go to trustable and certifiable AI for our paths. Second big idea is the steps towards autonomy. And again, I'd like to differentiate automation and autonomy. I must apologize for this slide to be a bit of a caricature, but I think we need to simplify a little bit. The upper arrow, you recognize the roadmap of UASs from extended surveillance to, as it was said by Fredrik, up to urban mobility. So that roadmap is commenced, right? And the sort of blue flash we have means that we have already gone to sort of breakthrough. We know the hurdles we have to overcome. We know the technology progress, but it's running. If you take the manned aviation, we see the bottom arrow, we know that we're going to assisted crew, and we plan to go to reduced crew, what we used to call single pilot operation, for example. And that will require a breakthrough. And the idea here is, I think, all of the progress we will do in technology for the upper arrow will benefit to the bottom arrow. And the smart thing here is when you consider our path, it can be a smart bridge between the two, because our path is a form of UAS, but in our path you've got the P, which is a pilot, right? So working in our path is sort of feeding the roadmap for UAS and preparing the future for manned aviation. Right, again, level of automation towards autonomy. Don't try to read that slide. I mean, you've got the classical 4 levels of autonomy towards autonomy of the US DoD. On the left-hand side, you've got the avenues of Europe for unmanned capability. The interesting here, because who in the world talks about autonomy? We've got ground transportation. We see the car industry. To be honest, and I don't want to be nasty here, the car industry experiences trouble here. Now, if you consider the railway industry, they're moving to autonomous trains, but of course, they've got to manage 1 dimension, whereas we have to manage 3 dimensions. But the big advantage we have is we know what safety is all about, okay? So we can leverage our background, to implement a sound roadmap. Probably not too fast, otherwise we will experience some issues, but we have the background. This is my message. And here, an illustration on how we could do that, because again, the sort of barrier of certification will be an issue. If you take an example of avionics software, how do you certify your software? Quite easy. You prove that it's safe because it's deterministic. You know every possibility that the software can deliver. That's the way it goes. DO 278, you have to test it to prove that everything is busted. So that raises an issue, because if you want to have AI, or if you want to have functionally rich software, perhaps you can't afford to do that. You can't prove that it's deterministic. So you have to think to something different. What could it be? Well, you could do this. You say, you define a normal behavior of operation, you encapsulate your software, and you try to track whether it gets out of its normal operation. If it's the case, then the green box system manager will take over. And that green box will be certified, all right? So, of course, that pushes the barriers of certification, but it's a very important thing. And the takeaway associated with that is, we're talking about new capabilities, and here not only technologies, but system engineering and system management, all right? So third was all about UTM. This smart picture gives you the sort of overall picture of the airspace, starting on the left-hand side with the civilian and air traffic management, moving to the right-hand side where the military like to control the operation in the airspace, and you have some security issues just in the middle, all right? And of course, it's a span of possibilities, regulation, and a mixture of low risk and high risk areas, okay? So here the idea is we have to move to integration of this airspace, but consider the airspace as an asset, but being flexible in low risk, low control, high risk, high control. And therefore, if you combine that idea to what I said before in terms of digital transformation, we believe the UTM should be a digital platform which gets all of the data which is necessary to prepare the flights and provide an API whereby you can create services which the user would subscribe upon and create added value on that digital platform. So you see to what extent the digital platform of UTM will be another way of providing access to the airspace as an asset, and eventually will be connected to the ATM and will transform ATM eventually. Now the last point I'd like to point out on UTM is you can't have US, we believe at least, you can't have UAS and RPAS in the airspace without controlling. And to control, you have to, I put it, counter UAV, or at least have a means of enforcement. And we see every time some issues, not necessarily very nasty, but some issues between manned aviation and US systems, all right? And one of the first things is, how can you detect those UAS? I heard some of us saying, do we need really to do so? Perhaps not everywhere, but around airports, we certainly need to detect. How do we detect UAS? Coming from the radar technology myself, it's not a given at all. And there are some technologies like what I put on the bottom right-hand side of the slide, which we call holographic radar, and which is a new technology that really enables to detect in the environment clutter some UASs, even if they're very small and very low. All right? So we have to put that into the journey and the roadmap of technologies. And with this, I will end up my speech, and thank you very much.
Thank you, David. I am old enough to remember that in the first generation of jumbo jet, Boeing 747, the crew was composed by 5 people: the captain, co-pilot, radio operator, navigator, flight engineer. And you know that along the years, 3 of them fade out. Now we have only the pilot and the co-pilot. What Pierre said is that manned aviation might progressively converge with unmanned aviation going to war through single pilot operations. You may believe or not, but you have any questions, you may ask Pierre, while I will give the floor to Alex, which is the last speaker, and Alex, kindly leave us some time for the questions at the end. The floor is yours.
Thank you, Philip. 那个皮尔先生先把吃晚饭的男。
I think I'm the only one that is standing between you and dinner, but I think we have a Q&A session, so I'm not the one that's standing between you and the dinner. So the topic for my speech today is our communication systems influence on aviation, especially on UAS and RPAS. Just including David and Pierre and Fredrik, all mentioned issues in aviation. Speaking about drones or UAS, for ID identification, the airspace control and the flight space, it can be harmonized in the management. It can be managed by different classes. But the fundamental issue is that what kind of enabling technology that we are using. So my presentation will be more communication oriented, whether we have communications that can change the fundamental technologies. Actually, you mentioned the core issues. I think it's similar to the ITS, that is the Intelligent Transportation System. Actually, we need an ITS for the space so that we can make the aircrafts more intelligent. In addition, we need to make the UTM system and the AI on board more intelligent, so that we can form a complete intelligent system for us to realize the goal. So in this process, we might give full play to the role of 5G. What I want to emphasize is that although we mentioned EMBB in 5G, but now we think that its influence on the transmitting of extra large space is very beneficial. Can we provide 1G bandwidth for the aircraft? Now we know that for an aircraft, it's only several MB or tens of MB, but can we just further increase it to 1G? If we can do this, it will be disruptive. And then for the hyper connection, especially you mentioned, Airbus mentioned whether it's possible that one pilot can operate several aircrafts at the same time. Actually, when we were discussing with our partners, we mentioned some possible changes in the space compared with the ground system. In the past, we used system to help people to handle the cars and aircrafts, but in the future, it will be the other way around, which means that the people will be helping the machines, which means that the major pilots will be AI instead of the humans. Of course, if we use this, we can operate several aircrafts at the same time, even during different periods of time, but it depends on the spatial communication. This is a test that we have done. On the left are the challenges of the drone supervision. These are long existing challenges. We are very concerned about the solutions. And in terms of aviation, there are many ways of thinking, many technologies, many approaches that you mentioned. On the right is our attempted solutions, starting from the takeoff to the flight, and then to the landing. So for network communication, we might have different needs in this process, but it's based on completely autonomous pilot or remote pilot. So there will be requirements. From our perspective, these network requirements can be realized very easily, and currently we have many successful tests. What I want to emphasize is that in terms of position, in the past, the positioning system and the communication systems are independent. They are separated. But for the digital twinning, we need the time reflects. But now in our digital system, we doesn't reflect the space. If we can reflect both space and time, which means the digital world and the physical world, we can make a real-time digital twinning system. So this bridge, we think, may be the possible 5G communication technology that mixes the positioning and communication capabilities. This is another test that we are doing. In this test, you will see that we have selected a region. This is a test with WADA on the drones. On the left is our map. That is the route of the flight. These are data that we collected in the test and the conditions of our test. Actually, for the test conditions, I think these can be done, including the ground system and the drone management capability. In the future, the same capabilities in scenarios such as mass application, for example, if we have tens of thousands of drones flying in a certain area, we can do this. On the right, you will see that we have a planned route to test the accuracy or correctness of the time and spatial reflection. And then we have a red part to test whether the reflection is correct or not, or whether the data are reliable or not. Overall speaking, the data collection and the support capabilities are within our expectation. It can well support the top layer process, including the flight control in the high space. So we think that through these tests and experiments and real flights, cellular technology can possibly, after being improved, be applied in the aviation industry. We're not promoting the standardization of 3GPP. We are putting the corresponding needs in our next plan. And now we already have the needs. And then on the right, we have the 4G current network or 5G target network. Especially in the 5G part, it can be 10,000 meters. So it covers not only the space below 3,000 meters. This is our structure. In this structure, you can have a clear view of the digitalization of the sky. So how can we build the basis for this space? How can we share the space? Especially with Thales and Airbus, we have shared with them our work. They both felt that we need a fundamental technology which is reliable to realize the complete UAS system. And so this is our pathway. I think the bottom layer of digitalization may be the foundation for the digitalization of the higher level or the top level. Thank you very much.
Thank you, Alex. So we have few minutes left for some questions. I have received around a dozen of questions. I don't know whether we will have time to answer them all, but may I promise that you will not immediately rush away after the closure. So if someone wants to approach you, you will stay here a few minutes. And then let's start with the first question. Probably two questions addressed to the entire panel. One says, how can states or ICAO approach the certification of autonomous technologies? And there is a question which is very similar, which says, your role reversal. If you were a regulator, what would be your first move? I believe these two questions are stimulating enough and are addressed to all of you. So let's try to answer.
It's a very good question, actually. I think there is a lot of different views on what is autonomy. And there's different levels of implementing autonomy. Autonomous vehicles doesn't, for me, necessarily mean that they are doing something that it's not according to the book. It's just another way of they are acting without getting the command from the pilot, or even more simpler. We saw today, or saw just a couple of minutes ago, about recognition of within pictures to identify aircraft. it's a mean of giving information also to pilots. So it's artificial intelligence within that already there. And it's also that we need to implement within some detection and avoid systems for optical. And their artificial intelligence is actually the way forward for that. So autonomous vehicles does not mean that they fly around, do what they like at the end. So I think ICAO can do a lot of defining or standardize the way of what we understand what autonomy is, and what we see today is allowed to be done, and also guidelines and work together with the standardization organizations how to certify all of this also. So I think it's a lot of things ICAO can do.
That's a very good question. I'm in the working group 3, DAA, where the autonomy was a big issue. When the aircraft is detecting something, and we ruled that the pilot on the ground has to command the avoidance maneuver with C2, but what if C2 is lost during the critical timing, that we allow the aircraft to turn, and we claim this is automatic. I don't want to restart the debate and then set back our Aerospace panel 3 times before, but there's an issue with this. As autonomy, we don't call it this automatic. Also, there was interesting question that humans are more complex, and that we just can't understand the human inside, but we allow human to fly aircraft, but why can't we fly the computer to fly the aircraft? And then I think that my answer about that was we can ask pilots about their intention. Normally, we can ask pilots what are the intention, even in a very difficult situation, but we cannot look into the inside of the AI computer and why are you doing this? We cannot integrate them. So I think in order for AI to be used in the mainstream, we'll need to understand more clear that what is going on inside, and we should be able to interrogate. And as being a professor, we are eager to give out the actual answers for questions. So if I'm a regulator, what is the best way to certify them? I think we can do that in a more of the statistical approach. We use a Monte Carlo simulation in a fast time simulation. We run 1,000,000 times the simulation and see how many times they fail. Then this is one of the way, and I don't think that this is the way we do right now. We certify the existing aviation systems, and also we can learn how we certify how we give the ratings to the pilots. So I don't think the AI is immediately the same as humans, but humans are. We can learn how we certify humans, and we can be able to apply those things to AI systems. Thank you.
I'll try a quick answer then. How to certify autonomous systems? I think we need to work together. Safety authority, industry, and research. We definitely are moving to a risk-based approach, as we all said actually. Low risk, law enforcement, high risk, mandated procedures. So we have to gather evidence of how we link the technology with the risk associated to that, and get a level of assessment of that risk and an acceptation of that risk, and then translate that into standards and procedures. But work together and be ready to revisit the way we enforce certification.
I think the core is one thing that is under the framework of ICAO, the regulation in the globe can encourage innovation. we can promote step-by-step or incremental progress of the projects.
For your answer. Meanwhile, more questions are coming. And again, I will not request you to respond to one individual question, but there are few questions touching a very important issue, which is security. Of course, any computer, any data link can be interfered. So how do you think that we could protect our future system from security threats?
Thank you very much. Actually, in our test, I want to briefly introduce our experience to you. We think that for security in aviation, it's critical, but this critical issue, when we're embracing new technology, it's greatly challenged because there are uncertainties. So for us, two levels of security are necessary. One is the security of the aircraft itself and its decision-making system. And second is the control and management system on ground. I think these two systems, the communication or a connection of these two systems is critical. If the aircraft is at any time connected to the ground, the interaction between the two systems will complement the weaknesses in each other. For example, the ground system is not detecting the problems as fast as the spatial system, while the aircraft system is not fast enough in mobilizing the resources on the ground compared with the ground system. So I think the communication between the two and the connection between the two must be reliable in order for us to ensure the security. That's why we think the bottom layer security connection is critical, because it's indispensable to improve the whole security of the system.
Let me try also a quick answer. First of all, security is not a matter of fencing. We think sometimes that we have to fence things and we're safe. Security comes from inside, all right? So the way forward is, as we did for safety, to do security engineering, to have natively to design our system with security, all right? And there are some technologies associated to that, but have to be articulated. And by the way, security engineering and safety engineering have to be put together, because sometimes security hampers safety and vice versa, all right? Another asset for security is, since the value is in data, what we have to secure is data, not necessarily the equipment that produces processes the data. Data has to be secure.
Security is a really big issue for Airbus, as it indicates, remotely pilotable through C2. So if some attempt is made to hijack the C2 link, one can send a same command to make the airplane fly into a wrong direction, and that is a very clear and present the threat. So we have to do all the things they could do in the conventional security measures, and also some of the latest technology like blockchains can be applied to it. The autonomous cars, many people talk about it, but they don't really have external command link, because cars, there are millions of cars out there. It's impossible to remotely drive it. But the RPAS and the small drones with the control box in our hand, there's always a chance for spoofing and everything. And the further, not only C2, there's other what they call the attack vectors. There's other issues about the the GPS issues, or many other the firmware, the more malicious attacks. Those are all present issues, and we have to think about it. In my project in Korea, we introduced the issue from the beginning, and then we are looking at a very serious look on this problem. And I think when our whole effort, including ICAO, we have to think this a more higher priority.
Well, I can't agree more than I agree to everything said before. I would like to add that, especially when we're talking about UTM also, the more connectivity we have, of course, the more issue the security will be, or cyber security will be. I think, however, that it's an issue that we have to deal with, but that shouldn't hinder hinder the development in any way, but it has to be taken care of.
Thanks to all, and if I may, there is another question on another facet of security, because it is not only security of communications or cyber security. And the question says, is there any security check for a person who purchases the drone, any background check? And on this, if I may, I will respond myself, because I know that the first rules on UAS promulgated in the world, which had an annex on the duties for security by the company, by the enterprise, the UAS operator, were the rules promulgated last year in Qatar. And so you consult that rules if you are curious. And furthermore, in the new Part 4 of Annex 6 to the Chicago Convention, there might be few paragraphs on the duties of the operator to ensure security. Instead, to the panelists, if I may, there are a couple of triggering questions, and you spoke a lot about robotic pilots and automation, but do you think that one day we may have robotic air traffic controllers or unmanned air traffic control?
There was actually a study back in 1990s, just before, today September 11th, but on September 11th, just before that, there was a very strong research on that, but after that event, it was all quenched out. But it is a very highly mathematical problem if you cast that way, and there is high optimization problem, so there was some effort on it. I think it's not, they don't really look at that direction. But UTM is, if I understand correctly, some of the, at least some segment, think that they assume cloud-based, more of the computing-based driven traffic management. So maybe that can find its way back to ATM, and then I think the ICAO mentions that someday ATM, UTM merge into some future XTM. So I think that's possible.
Okay, so I might add something. UTM stands for UAS Traffic Management, which is not UAS Traffic Control. Some colleagues confuse air traffic control with air traffic services, with air traffic management. But we may have air traffic management even without air traffic controllers. And we will have fun in the future. Maybe that there is one last question we can address to the panelists. What about detect and avoid at very low altitude? What about detect and avoid at very low altitude?
Yes, I can start with that one. As I said in the presentation also, there, for the lower altitudes, we see that UTM is especially, it's an enabler, it's a means that is required. There are some issues that I mentioned about, especially the platforms where we are looking at operating in the lower altitudes. They are smaller. Even the cars are relatively small and compact. And it's very difficult to integrate a detect and avoid system capable of detecting non-cooperative aircraft. And to make that happen with the non-cooperative, the system will be so heavy that at the end, the aircrafts will not be able to, it will not be a business case for many of them actually. And for that, UTM is an enabler, and it's very important. It has to do with especially, I think Mike Lesson talked about that today also, it has to do with separation minima at the end also. And therefore, at the lower altitudes, we recognize, especially at Airbus, that we need a UTM system. And if we don't have the UTM system, we need to talk about separation minima.
Yeah, I'll be brief. Last week in our school, we flew 130 drones at the same area, and I saw them colliding in the air. So they do happen. I saw it. Just like a big airplane, I think it's same. It's like the construct level, traffic management level, and in situ level. They have to be dealt that way. But I think it was mentioned before, ADS-B cannot be used. We need some other way. I think of HUAWEI's presentation. We need to have a new way of the ADS-B-like system to broadcast their location, and they need to have onboard sensors like vision or some of the laser detectors to detect something's around and try to get around the obstacles. Thank you.
Yes, low altitude detection and avoid is a difficult technical problem. I think a multi-sensor approach could cope with it. There are a lot of research being done, in particular by the military, so we'll see if that can flow down to US and Aerospace. And remember, there is a balance between what we can achieve in terms of technical performance and procedures and rules, so we can balance the two. That could be another avenue as well.
I'd like to add that there are many outstanding technologies in low altitude. I believe that for the anti-corrosion system, but if we want to utilize the UTM system, for example, to restrict the spectrum and the height of the UAVs, and if the UAV can fly based on the order from the ground and from other parties, I think it is a better way for us to do that.
Thanks to everyone and thanks to you. Unfortunately, time is over, and I have to kindly ask you to forgive the panelists and me, because we have triggered your attention. We have received few more questions, which we have no time to answer, but I can promise that neither the panelists nor me will immediately rush away. So once we close, if anyone wants to ask further questions, we will be here for a few minutes, available to interact with you. Thanks for your attention, and I believe that now I should give the floor back to, back to my masters in ICAO.
Thank you, Filippo. Thank you to Filippo and to each one of our speakers for those exciting and informative presentations on the state of technological innovation and in academia and in industry. In terms of legacy, I think I learned that our moderator invented the quadcopter with Leonardo da Vinci. Before or after the Mona Lisa, I'm not sure, but anyway, that brings us to the end of day 2. Thank you all for your participation. Go enjoy your evenings. We'll see you back here tomorrow for day 3, and I'll just ask that the first session of tomorrow, that's RPAS operations, impacts on other stakeholders, please come to the front before exiting. You have a meeting with your moderator. Thanks very much.